Okay, so I think we can continue our discussions. It's supposed to be finishing the chapter 13 for today's class. So it's just a review for what we have done. We have done at least several formulations for the curvature, including the last one we did, okay, the curvature, and then we also have some another formulations if we are using the calculation of curvature in just a simple function y equal function of x, and we can immediately exchange the functions in terms of vectors which has the x-axis as parameter and f of x just as in its y-axis, and thus we have the it's actually derived from the same formulations as we did before, but we are changing all with the terms of the function of x. Okay. And lastly, we have at least define the normal and binormal vectors. So normal vectors, as I mentioned, is supposed to be orthogonal to the unit tangent vector. So normal also it's also a unit vector. So it's supposed to be having relations with the derivative of the tangent vectors, okay, because it's supposed to be orthogonal. And how we are going to visualize? So actually, as long as we can make sure all three components they are intact and they are consistent, like the tangent, the normal, and binormal, they always have some consistency. Then it's fine. Okay, it's fine. It's okay to draw or to visualize like that. So whenever you have, maybe you draw a little bit shifted, but as long as, for example, if your normal is going here, then your binormal should go and take adjustment. So it should be okay. We call this in terms of usually when we are dealing with some, especially in terms of observing the mechanics of some materials or some devices, we are going to take some points and then we take it as these three components, as the tangent vectors, the normal, and the binormal. Okay. And we define the normal and binormal as we did in these formulations. And we can also imagine if it's moving. So as long as you have those consistency, okay, you change the movement, you change the position from this point, you're moving here, and you see that because its tangent is changing because of the curve, it's following the curve. First is this one, and the second one goes here. Then the implication is the normal also changes. So and when you change the normal, you change also the binormal. Okay. So the first unit vectors that we need to visualize is the tangent vector, because you can apply it into the curve. Okay, let me give you a brief example on how the calculations will be. So the question is asking, find all these three components. So this should be a typical questions for the chapter 13. Or maybe also the curvature. Okay, to start with, the tangent vector will be related to the first derivative. So we are going to have our first calculation on the first derivative. That will be our first steps, and take the magnitude. Okay. And we can factorize this part. So we will have 1 over t squared and we take the positive one because of the t squared plus 1 is always positive. And now with these two value, we'll have the unit tangent vector as the r prime divided by its magnitude value. Maybe we can simplify. That's the unit tangent vector. So we start from the unit tangent vector, and then from unit tangent vector go to normal vector, and then go to the binormal. Well, we can find the point. Okay, we are having the point at 1, 0, and 1, and according to the vectors, to the vector functions, that the t should be equal to 1. So we can evaluate the functions at 1. So this will be half. Okay. And then we can also derive the tangent. Derive the tangent. So when we derive the tangent, we are going to take product rule. Okay. So the scalar and the vectors. So we take the scalars first. And then plus Now we can take it at t equal 1. We can calculate. So 2 minus 1, 1 square root of 2 is 0. 0 minus minus 1 is positive 1. And we can also find its magnitude value. So half square root of 1 plus 0 plus 1, or square root of 2 divided by 2. And from here we can take it into our n, or n1. We directly write n1 is t1 divided by t prime 1. Will be half square root of 2, so we will have 1 over square root of 2, 1 over 1. Okay, so we find t, we find n. Let me put here okay, that's n, and then we need to find the binormal from the cross product. So we can take, and then t is 1 square root of 2 minus 1 cross 1, 0, 1. Now for the cross product, you can do the crossing using the determinant of matrix, but actually it's up to you. So will be square root of 2 minus j and square root of 2k plus j should be square root of 2I minus 2j square root of 2k. Okay, so we have square root of 2 minus 2 minus square root of 2. Or we can simplify it. This will be our B1. Okay, so that's B1. And the curvature, we can write down the formula for curvature at t equal 1 using this formula. We will write here for r prime 1 is equal to square root of 4 or 2. And this will be equal to square root of 2 over 4. That will be the curvature. At least if you have a typical problem like this, I hope and I expect you to deliver the problems or deliver with the with this kind of answers. Okay. So you have vector functions, derivatives, connect to the unit tangent vector, and then the normal vector, the binormal, and also the curvature. Because all is connecting to the derivative of the vector functions. Okay. Okay, so basically, we are having a three important vectors, which is the tangent, the normal, and binormal. Okay. And since these three axes or these three vectors, they are in alignment with each other, okay, we can also relate all these vectors with the plane, okay, with the plane they are in. Okay. So for example, the normal vectors and the tangent, they are in one plane, and that plane is specifically, we can call them as a normal plane, and they are also plane that align with binormal. So if we take the the previous one should be osculating plane, and the normal plane is the one that is aligned with binormal. So if we are going to take the picture, it should be like this. So supposed to be the normal plane, as in definitions, it's supposed to be a plane that, or all vectors in plane that is orthogonal to T. Okay. So we know that the normal is also orthogonal to this 90 degree. This is also orthogonal to here. So all the vectors that is in this plane, that all they are all orthogonal to the tangent line. Okay. And the other plane is called the osculating plane. So osculating means it came from the osculum, or kissing or touching. So it's actually a plane that is close by, or the closest to the part of the curve near the point P. Okay. Or simply, for simplification, to simplify, the oscillating plane are usually along with the curve. If the curve is here, it's plane. We call the oscillating plane. That's the easy definition. And the second picture that I think also important in this sections is we have we call the circle of curvature. So circle of curvature, or we name it the osculating circle. So actually, this circle of curvature, or the osculating circle, they are with the same property as we have seen before. They have the same normal, tangent, and binormal. But we are focusing more on the normal here, because it's the definition for the circle of curvature. The radius is 1 over curvature. The definition, I think we also mentioned last time, when we have the circle, the small circle, the large circle, right? Which one has the largest curvature? So means that when we deal with this, we have the radius is 1 over curvature. And it's aligned with the direction of the normal vector. So we can actually visualize how the curvature will change when we are moving the point. And as you can see, it's the same as we did last time when we compare the small circle and the large circle, because it's 1 over curvature. Then when you have a small circle, it's going to be compared with the big one, then should be reciprocal relation. Okay, let me give you an example on how to define or to find the plane, the normal and osculating plane. So example, Imagine a helix with a vector functions of cos. Okay, before going to the normal plane and the osculating plane, let's just define the tangent vector and the normal and binormal from this helix. So first we derive the vector. And we get the unit tangent vector is we take derivative of tangent vector. And take its magnitude value. So it's just 1, so it's just 1 over square root of 2. So we have the normal should be just negative cos t I plus sine tj, right? And the binormal, we have t cross n t is minus sine cos t and 1. Cos t, and the n is minus cos t sine t and 0. Oh, it should be minus also, sorry. Should be minus. Okay. We can compute. So we will have 0 minus cos tj plus sine squared tk and then minus cos squared tk minus sine t I, and then the rest is 0. So we will have this become 1. So we will have sine t I minus cos tj plus k. So this will be our binormal. The scalar is 1 over square root of 2. And this will be the vectors. Okay, we find t, n, and b, right? Okay. So the follow-up questions, find equations of normal plane and osculating plane. Of helix at 0, 1, pi over 2. If we take the R, then it's correspond to t equal pi over 2. Okay. And if we take the derivative and put pi over 2 inside, we will get negative sign. It's -1. This cos pi over 2 is 0. And this will be 1. And remember that the R prime is a normal factor to R, right? Okay, this is orthogonal. So remember the normal plane equations, plane equations in the chapter 12. So the equations of normal plane. We are using the normal factor -1, 0, 1 as a direction, as its direction. So -1, and x minus 0. The point that we are going to approach, 0, 1, pi over 2. And then plus 0. And then plus 1, z minus pi over 2 is equal 0. And we are going to simplify, or z equal x plus pi over 2. And this will be the normal plane. So in practicality, you need some formulations from chapter 12 for especially the equation of plane. And how about the osculating plane? So basically the idea is to find which one is normal to which factors. So for example, if you take here the oscillating plane, it's contained this tangent and normal, right? It's contained t and n. So we need to find the factor that is normal to this two, which is the binormal, and that is our approach for the plane. So we will have the binormal as it is the cross product of t cross n, right? And we already have calculation for its binormal, which is 1 over square root of 2 sine t, negative cos t, and 1. So at particular point pi over 2, we can write down the whole formula, that is with this factor b. And if we look at factor b, if we just take a look at the factors and we take out the scalar, we have a vector 101, right, that is parallel to b. So we can use this 101 because it's normal to the plane. It's a normal to the plane orthogonal. So we are using it. That's the same principle with this. So we are going to have. So maybe we write down some explanations that 101, we are going to use 101 as our directions because it's parallel to B. Okay. So we are going to use it for 1 x minus 0 plus 0 y minus 1 plus 1 z minus pi over 2 based on the point we have in the questions. So we have x plus z minus pi over 2 equals 0, or z is minus x plus pi over 2. Okay, let me recap what we did here. So first for the normal plane, let me go in detail here. So for the normal plane, the normal plane is, so we have the tangent, the normal plane here. Right? So how we are getting the normal plane? We are using the fact that the r prime is a normal vector with r. Okay, so we are going to use the direction of this r prime into our equation of plane. It is direction of our vector. It's orthogonal, right? So we are using the negative 1, 0, and 1 from here. Okay. And then the point we are going to evaluate is 0, 1, and pi over 2. That's according to the information. Okay. So and then we get the normal plane. The normal plane is here. The rest, or the second question is oscillating plane. Is the plane that's along the curve. The plane that along the curve, because the oscillating plane, it has t and it has n. We need to find its normal, which is the binormal, right? So we are going to use the binormal. For example, in our case here, when we are evaluating at our pi over 2, we have 1 over square root of 2. Actually, this is here, so we are having 101, right? 101 from this pi over 2, 101. So we are going to use this vector 101 as our direction because it's a normal to the plane. Okay? It's normal to the plane. We are going to use that. So we are going to use this 1 over 1, and then we are import all the information. 0, 1, and pi over 2, and we're getting the oscillating plane. Okay, I hope it's as in chapter 12 we have done. I hope it has some correlations that you can take advantage of, and actually because it is also vectors, so we are going we are not having much trouble or problem hopefully for this case. Okay, as a summary from the unit tangent, normal, binormal, and curvature, we can write some formula. This thing essential for this part. Unit tangent vector, and then we have the normal, we have binormal, and we have the curvature that we are actually defined from. We have the unit tangent, and we derive unit tangent with respect to the arc length. Okay? It's from the arc length, and then we can write as in T prime and we can also write in terms of at least this is the essentials for chapter 13. Okay, the next sections, I believe the last section on chapter 13 will be about the torsion. So in the simple definition, torsion means there is a twist. Okay, there's a twist. Okay, we have a short break. So, okay. So 14.1, I have uploaded into, I think already announced on the Moodle. So you need to watch and see. So up until the chapter 13, so basically, this is the summary, okay, the formulations that essential in chapter 13. Okay. So let me write this as essential formula, and also the torsion that we are having the we are having the dB over ds, and let's observe dB over ds in terms of change in the oscillating plane, and we have formulating the torsion formula, and this is also essentials. Okay. Well, you can also try the second formula if you want, but I think just the first one is, I think, enough. It's already enough for a basic for torsions. Okay. All right. So we can start a new chapter. So chapter 14 means that next week we will have quiz for chapter 12 and 13. Okay, so do you want quiz on Monday or Friday? Friday, okay. Okay. Okay, so chapter 14, 14.2, 14.1, I gave you in the video, so if you haven't watched, you can watch. But that's just introductions on how we are using the terminology, how we are using the graphs. Okay, so instead of we are having one variable, we are now having two variables, and we are writing as usually if we have two, we have function of x and y. So for example, if we have functions, this is sine, and then x squared plus y squared. And we have another one. Let's say we have g. And we approach as x and y approach 0, and of course therefore the xy point is approaching the origin, right? And if you're using the table, for example, table checking the 0, 0.3, or maybe negative 0.2, 0.5, and so on and so forth. The first one seems that if we check the limit, seems that this one is getting 1, and the other limit doesn't exist. Or we can write in generally as limit of x and y approach a b of f x y, it's equal to some L. So we can make values of the function close to L as with taking point of xy close to the point A, B, but not equal, okay, but not equal AB. And in more precise, if you remember the limit, so let f be a function of two variables whose domain D includes points that arbitrarily or closer to A, B, then we say limit as xy approaching AB fxy equal some L for every number epsilon that is positive. It means that the distance that is close to for the functions. So every epsilon there is number delta that is also positive for the xy, such that if xy is in its domain and the delta is the distance between this, so instead of just x or y, we are having a distance between 2 points. Okay. Sorry. As its distance. Then the difference or the distance between the functions and the L will be less than epsilon. So it means that the epsilon and the delta is the small gaps between the point that we are going to approach. Okay, so if we approach from xy to AB, means that we're having some small delta in between those xy. Okay, and because of those delta, the implication is we have a small epsilon that is in between of the functions and some constant L. Okay. If we draw the domain, for example, domain is here. Domain D. And let's say this is the origin. And let's say we have another small domain inside the large domain. And that is what we have. So let's say this is XY. And we have the delta, in which this is the AB. This is L plus epsilon, L minus epsilon. So if we slice our graph and make it into XY plane, and we are going to have our domain, and we have a small domain inside of the largest one, and that is to the notion the delta. So when we have this point, and we are going to take the implications will be into our z-axis. So usually the functions, if we have two variables f, x, y, the f, x, y is the z. Is the z. We can also imagine that this is our z. Okay. So the implication is in our z we will have some L that is applied from the our domain here, and we have the epsilon, the distance epsilon in between is L. Taking our times to see the function itself, because it's having x and y, the functions will be our surface here. So when we have the domain from here, so we will have an area of small domain here that is, so actually what we are looking for is our AB, it is this point here. But to see the implications of the delta, so we have, or we should imagine this D here, the area is really small, So when we are taking this into our function, we are having an implication that is, this will have the epsilon. This is to know that the limit is not the exact number, it's just our approximation, our approach. Okay, now we are going to see why this limit doesn't exist. Okay, let me go through the new page, new sections. So let me write the some notes. So if the functions of xy is going to have L1 as it's going to closer to AB along path C1, and fxy is going to closer to L2 as xy closer to AB along path C2, where L1 and L2 is not equal. Then limit of xy doesn't exist. Okay, what does it mean? Okay, what does it mean? So recall what we have done before in limit in calculus 1. So limit as x approaching a, remember from the left, if we have not equal from its right, then limit doesn't exist, right? Okay, so I think all agree with this calculus 1, okay, our review. But then if we have x, y, they both approaching to some point or AD, okay, point AD, how we can imagine it? If it is just left and right, I think it's easy to be visualizing in our mind. But what if we have two? So if we are having an CD, these two axes, and if we take this is our AB, okay, we can approach AB from anywhere, right? We can approach AB from here. We can approach AB from here, and from here. And we can make in any random way we have, right? So this is a little bit complicated. So we have we can approach AB from an infinite number of directions in any manner as long as the xy within the domain, right? Within domain of the functions, okay? So then, that's why we are going to have this path, C1 and C2 as our notions. And C1 and C2, it can be any curve. Okay? It can be any curve, but simply we are usually taking C1 and C2 as a simple curve that we can imagine. Maybe a line equation, maybe it's a vertical line. That is, we can take it into our calculations. And when this is having two different conclusions, means that it will be non-existent. Okay? But if we take this different path and we take it and then we resulting same results, L1 is also L1. The limit exists. Okay? The limit exists. Okay? So we are going to approach within those different paths. So take the limit. Okay. So let's approach first. Let's approach this 0, 0 along x-axis. So if we approach along x-axis, just x-axis means that y equals 0. So we are going to use y equation y equals 0. Means that y will be fixed constant 0. Okay. So y will be 0 for every point in xy. So the functions become fx0. X squared over x squared, all this is equal 1. Okay. So then the functions will be approaching 1 as the xy approaching 0, 0 along x-axis. And then the other part, we can approach along y-axis. So x will be 0 for every xy. So 0y, this will be negative y squared is negative 1. So f of xy will be getting closer to negative 1 as xy getting to 0, 0 along y-axis. So since it has different results, then we can conclude that limit doesn't exist. But sometimes these two approaches may be not enough. You need another path. Okay. So x-axis, y-axis, and maybe the other one is using the line y equal x. That's also easy path to imagine. And you can just exchange x to y or y to x, and you can compare those results whether it's equal or not. If it's not equal, then the limit doesn't exist. I think I will just stop until here, and we will continue later.